So in class, we worked on rational functions, and instead of really looking closely at their graph, I mean, we've seen a reciprocal function, which looked similar to the graph that we see here, but not exactly, because you can see that the equation is different. And then what we also did is we looked at some really complicated looking rational functions. So they had a polynomial in the numerator and in the denominator, and we looked at what happened at the end behaviors. So remember, kind of, if you look at that handout that we went through in class, you can see what the values approached the first set of equations, the second set of equations, and the third set of equations. And we talked about how each of them were different. Okay? And what those were telling us is what the y value of the function was at the end. So like in this function right here, I would see that this is approaching this towards one end, and also it's approaching the same number from the other side at the other end, and it looks like that number is 1 right here on the y-axis. So I would assume that it approaches 1, and that makes sense because if we look at our equation, these have the same degree, and they each have a lead coefficient of 1. In this second graph right here, I would assume that this graph has no horizontal asymptote or no end behavior towards one number because it continues to grow upward and downward. That makes sense because if you multiplied out this equation, you would get a degree of 2 in the numerator and a degree of 1 in the denominator, which means the degree of the numerator would be higher, and that was the case where we saw the functions didn't approach any certain number and they didn't have any certain asymptote. Now in this first example, okay, again, the graph looks a little different than what we've seen, but it seems like everything kind of evens out to this right here and starts to follow that asymptote, which makes sense again because in this function they have the same degree. So we would use the lead coefficients and create our horizontal asymptote that way. So this is just a note of all the things we're going to talk about while we're doing this. So we've talked about vertical asymptotes from the previous lesson. The investigation we did in class had to do with horizontal asymptotes. We're going to talk about oblique asymptotes and holes while we're going through this. And we've talked about how to find x and y intercepts before. So you should use this page to come back and make notes on any of these things as we go through. So here's our first equation. We want to graph it. We want to identify asymptotes, intercepts, holes, domain, and range. So it's going to help me, if possible, to factor this function. So my numerator does not factor. But in my denominator, I can factor out a 2x squared. And that leaves an x plus 2. So how this helps me, remember that our vertical asymptote was when the function is undefined. In other words, when the denominator is equal to 0. We can see that there are 2 factors in our denominator. So that's 2 ways that our denominator could be equal to 0. If 2x squared is equal to 0, or if x plus 2 is equal to 0. So this gives me a vertical asymptote at 0. And also at -2. Now notice I don't just write the numbers, I write the equations, because those are equations of lines. So here's my vertical asymptote at 0, and my vertical asymptote at -2. Then I can go to find the horizontal asymptote. And that has to do with that handout that we looked at in class. So if we look at the degree of the function, the numerator is of degree 2 and the denominator of degree 3. This means the denominator has a higher degree, and in that case, if you look at that handout, we determined that with horizontal asymptotes, if the denominator has the higher degree, the horizontal asymptote is at y equals 0. So we have an asymptote here. Now remember, the vertical asymptotes serve as kind of dividing our graph up into sections, whereas the horizontal asymptote just shows us how the graph should behave at the very end. Because I have a horizontal asymptote, that means I do not have an oblique asymptote. So an oblique asymptote would be some sort of curve or line that's not horizontal that your function follows at the end. So you only have one or the other. It either follows a horizontal line or it doesn't, and then you go find an oblique asymptote. A hole in our graph would occur if there was something that's like a vertical asymptote, like these factors that we saw in the denominator, but one got canceled out. And since we didn't have any factors that cancel here, we don't have any holes. Then we had talked about finding intercepts. So we want to look at x-intercepts as well as y-intercepts. Now remember, intercepts are found by setting part of the equation equal to 0. To find the x-intercept, you set the y value equal to 0. So essentially, you're taking the whole equation and you're setting it equal to 0. Since these equations are fractions, the only way we can get a fraction to be equal to 0, not if the denominator is equal to 0, because that would be undefined. So it really just depends on the numerator. So when the numerator is equal to 0, that's when we'll have x-intercepts. So rather than having to set this whole fraction equal to 0 all the time, what I'm going to do is take the numerator and concentrate on when that would be equal to 0. So I'm going to go ahead and solve this equation. So I get x squared equals 1/2. X equals the square root of 1/2. And if you rationalize the denominator, that gives you root 2 over 2. And I took the square root of both sides, so I need to make sure I include plus or minus. This means there are two x-intercepts, one at root 2 over 2, 0, and one at negative root 2 over 2, 0. Now for the y-intercepts, all we're going to do is plug in 0 for x. So we're going to take our equation, and everywhere there's an x, replace it with 0. But you can see that that makes the denominator equal to 0, so that's undefined. So I wouldn't expect to be able to have any y-intercept in this case. So I'm going to go ahead and put those x-intercepts on the graph as well. I'm going to use a calculator just to give me a good approximation of what square root of 2 divided by 2 is. So on the calculator, I see that square root of 2 divided by 2 is about 0.7. Okay. So I have positive 0.7, 0, and negative 0.7, 0 for my x-intercepts. Now to graph these functions, we could plug in points to figure out where things are, but we can also use this thing called a sign chart to figure out whether things are above or below the asymptote. So what I'm going to do is I'm basically going to take a snapshot of my x-axis, and I'm just going to mark anywhere that there's a vertical asymptote, because that divides up my graph, or an x-intercept, because that's a place it crosses the x-axis. So I have this at negative 2. I have my x-intercept at negative, like 0.7, because that was our root 2 over 2. I have another asymptote at 0, and then I have another intercept at positive 0.7. So now I'm going to go ahead and go through, and I'm going to analyze the signs. And what I mean by the signs is I'm going to think about how my function is set up. So I basically have y equals negative 2x squared plus 1 over 2x squared times x plus 2. And what I'm going to ask myself is if I plug in a function in this range, so a number that is less than negative 2 as an x value, does the function turn out to be positive or negative? So the way I'm going to look at this is kind of, does the numerator turn out to be positive or negative, and each factor in the denominator to make that decision. So if I'm looking at numbers less than negative 2, say I pick negative 10. If I plug negative 10 into this numerator, first I would square it. So that's going to make like positive 100 times negative 2 would be negative 200 plus 1 would be some negative number. Okay, that's all I'm looking at. If I plug it in here, it's squaring the negative is going to make a big positive number. And if I plug it in here, the negative 10 or whatever I'm plugging in that's smaller than negative 2, when you add 2 to it, will still be negative. So what I see here is that the denominator of my fraction would be negative, and a negative over a negative would be positive. Okay? That means what I expect on my graph is everything on the left side of the axis should be above the x-axis. Okay, because it's saying all the points there have positive y values. Okay? So then I'm going to do this again, and this time I'm going to do it with a number in the next space that I need to look at. Oops. Okay, so a number between negative 2 and negative 0.7, maybe I would do something like negative 1. Okay? So if I plug negative 1 into the numerator, then I'm going to get a negative. If I plug it into the first factor of the denominator, it turns positive, and in the second factor is also positive. A positive times a positive is positive, and a negative divided by a positive is going to be negative. So that means in this area here, I expect my graph to be below, just between the asymptote and the x-intercept. And then the question is, does it cross through the intercept and go above? Or does it turn back around and go below? So then I need to test a number that's between negative 0.7 and 0. So maybe I test something like negative 0.5. So if I plug negative 0.5 into this first one, so negative a half, it's going to be 1/4 times negative 2 is going to be negative 1/2. It's going to be positive in the numerator. And then it's going to be positive here in the denominator and positive here. So all those positives are going to make a positive, which means once it's going to cross through that intercept, and then it should be above the x-axis, just between the intercept and the asymptote. And then I'm going to plug in a number between 0 and 0.7, so something like positive 0.5, which again here is going to be positive, here is going to be positive, and here is going to be positive. So that's going to create a positive. So between 0 and 0.7, I expect it to be above. And then I'm going to plug in a really large positive number, something bigger than 0.7. And so when I do that, this numerator right here is negative. Everything else is positive. So this is going to give me a negative result, which means after the intercept that's right here, I expect everything to be below the axis. Okay, so remember that we need to draw in a curve that goes above and below in the right spots, and also follows the asymptotes at the end. So like this section here that says above, I expect my graph to follow the asymptote and then go up this asymptote. Because it's supposed to follow asymptotes, it has no x-intercept, and the whole thing is supposed to be above. Now, in between the two asymptotes, I see a below first, which means I'm guessing I follow this downward, but it ends with above, so here it goes upward. And I know it has to cross through this x-intercept, so my curve is going to go something like this. Then in the next section, it says above, and then I hit the x-intercept, and then I'm below. So it's going to be above, I hit the x-intercept, and I'm going to come below. Now here's where we encounter a small problem. I don't know what really happens below, but I know I'm supposed to end by following this asymptote out here, so it's got to eventually curve back around and go like that. And I'm just asking you guys to make a sketch right now, so that would be fine. Okay? So there's kind of a lot involved in each of these problems. All right, so we're going to look at another one. Again, we're going to go ahead and factor, and the numerator has been factored for us, which is nice. And in the denominator, see, we're going to have 2x and x. That would make 2x squared, and 3 and 1, negative and positive. All right, so everything's factored. So vertical asymptotes. Set your factors in your denominator equal to 0. So we're going to have two of them. 1 at x equals 3, 1 at x equals negative 1/2. Remember, those are equations of lines. They should say x equals. All right, then we're going to look for our horizontal asymptote. So in this case, they have the same degree. If you multiplied it out, you'd have x squared as the highest value. And in the numerator, you'd have a 3x squared as the first term, and in the denominator, a 2x squared. So you're going to use the 3 over 2 as your asymptote. So y equals 3 over 2 is our horizontal asymptote. That means we have no oblique asymptote. And then for holes, none of our factors canceled out, so we don't have any of those. For x-intercepts, remember we're just now looking to set the numerator equal to 0 now that we understand this idea a little bit better. So that means there's two factors here. 3x could equal 0, or x minus 1 could equal 0, which give us x-intercepts at 0, so 0, 0, and as well as at 1, so at the point 1, 0. So at 0, 0, as well as at 1, 0. For y-intercepts, that would be plugging in 0 for x. So if we did that, we would get a value in the denominator, but because of this 0 in the numerator, we're going to get 0, so our y-intercept is also just 0, 0, which we already have on the graph. All right, so now we're going to look at our sign chart. Okay. And remember, our goal is just to divide up the x-axis according to asymptotes and intercepts and see what's happening between them. And remember, when I say see what's happening between them, what we're really looking at is we're looking at all these factors that calculate y that are in the function and seeing if they turn out to be positive or negative to tell us if the overall result for y will be positive or negative. So the first thing we would do is plug in a number smaller than negative 1. So when we do that, that's going to be a negative, another negative, a negative, and another negative. And if you work all that out, you get a positive, which means I expect everything here to be above the x-axis. You don't have to write the words above and below. I'm doing that for your notes so you can understand some context. All right, then if we look at the next number that we're plugging in, something between negative 1 and 0, like negative 0.5, we'd have a negative, a negative, oh, sorry, I marked our asymptote wrong. Okay, so our asymptote, according to my graph, at a point it looked like it was at negative 1, but it was at negative 1/2, like we said right here. So this should have been negative 1/2. That doesn't change the first part because we still plugged in a really negative number, but I can't plug in negative 0.5 clearly for what I was just talking about. I need to plug in something like negative 0.3, okay, something that would be between 0 and negative 0.5. So that would be negative and negative. This would be positive, and that would be negative. So in the end, that's all going to result to a negative. So here, I expect it to be below. And then between 0 and 1, if I plug in something like positive 0.5, this is going to be positive, negative, positive, negative. So in the end, that's going to work out to be positive. So I expect everything between 0 and 1 to be above the x-axis. Then if I plug in something like 2, something that's between 1 and 3, I get a positive, another positive, a positive, and a negative. So that's all going to work out to be negative in the end. So here I expect it to be below the x-axis. And then after that asymptote at 3, if I plug in a very large positive number like 10, I'll get positives for all quantities, giving me a positive result and saying I expect to be above the x-axis. Now when I go to graph this, in the middle section, see how you're below, you hit an intercept, then you're above, you hit the intercept, and you're back below? That's some sort of, I'm going to say like a parabola, but not a parabola because it clearly isn't symmetrical, but it would turn around like that. Now, out on the outsides where it says above, even though I'm above the axis where this is written, I'm not above the asymptote, which is okay, except for I don't think I want to draw the curve here because then it would end up going downward, which means it would eventually be negative, and it would cross the x-axis, and we don't have any intercept marks there. So here, where it says I need to be above the axis, kind of analyzing what my options are, if I have to follow both asymptotes and never cross the x-axis and stay above it the whole time, then this branch needs to be up here, as well as this one over here. Okay? All right. Okay, so the next one we have 5x squared divided by 3 plus x. So our vertical asymptote, again, set the denominator equal to 0. We get x equals negative 3. For our horizontal asymptote, we don't have any because the numerator degree is greater than the denominator, which means we have to find an oblique asymptote. To find oblique asymptotes, we actually do division on the problem. So we have 5x squared being divided by 3 plus x. Now, I'm going to write everything in order, and I'm going to make sure everything has a power of x from the highest power it has down to a constant. So I'm going to fill zeros in there and do division. So I'm going to ask myself, what times x equals 5x squared? So that would be 5x, which would give me 5x squared plus 15x. If I subtract all of this, I get negative 15x, and And if you want to write it, you have a plus 0. So then you're asking yourself, what times x would give us negative 15x, which is negative 15. So we get negative 15x minus 45. But again, we're subtracting all of that, so that just gives us a remainder of 45. Now, here's the thing about the remainder. Remember that oblique asymptotes and horizontal asymptotes are designed to describe the behavior at the end of the function when you plug in like really big numbers. If we plug in really big numbers, this denominator here is going to get really big, which means the fraction itself is going to get closer and closer to 0. So this part doesn't end up mattering to us, and we take this other part, that equation, as our oblique asymptote. So our oblique asymptote is the equation of a line that is y equals 5x minus 15. So if I put my vertical asymptote and oblique asymptote on here, there's my vertical asymptote at x equals negative 3. And I'm going to go ahead and number my y-axis by 5s, okay, so that I can plot my negative 15, and then a slope of 5 is up 5 over 1. I know it looks like a slope of 1 over 1, but we scaled the axis, so just be aware of what it is and what it isn't. Okay. Now, this means our graph is not going to follow like horizontal stuff at the end. Instead, it's going to follow these lines shooting up and shooting down at the ends. Okay? There are still no holes because no factor was canceled out. For our x-intercept, if we set the numerator equal to 0, we would just get 0. And for our y-intercept, if we plug 0 in for x, you'll see that we also get 0. So our y-intercept is also that 0 over 0. So we cross right here. All right, so again, we're going to go ahead. We're going to do our little sign chart. So we're looking, negative 3 is where our asymptote is, and we have an intercept at 0. And that's it. Our oblique asymptote isn't dividing up our x-axis at all. It's just these places where it crosses or is undefined. Okay? So when I plug in numbers smaller than negative 3, I'm going to get a positive. Oh, this should have been squared. Sorry, you guys. When I plug in numbers smaller than negative 3, I'm going to get a positive over a negative, which is going to be negative. Okay? So here I expect everything to be below. When I plug in numbers between negative 3 and 0, say something like negative 1, I get a positive over a positive. It's all positive. And when I plug in positive numbers bigger than 0, I also get all positives. So here I expect it to be above as well as here. Now, remember that this vertical asymptote is like your dividing line. So right here where it says below, if I'm supposed to follow the oblique asymptote, that means I'm either here or on this side of it. But I'm also supposed to follow the vertical asymptote, so I'm either up here or down below. So let me just give you a picture of what these often come out to look like. Either like this curve that you see down here low, or it follows this one up here. Now the reason we can't be that second one I drawn that goes upward is because 1, we said below, so we're supposed to stay below the axis the whole time. And 2, we don't have another x-intercept on this side of the asymptote, so we shouldn't cross the x-axis. So I'm going to choose that branch. Now, when I go to graph over here, that means that I kind of expect something either in here or along here for the right side of the vertical asymptote. Now, given that everything was above, this one that's down below is probably not going to work. And then I have to take into consideration my x-intercept, which is right here, and clean this curve up a little bit. So I know it's supposed to hit that x-intercept, but it's supposed to stay positive on all sides of it. So it shouldn't go below the x-axis. It should follow the asymptotes, and it should hit that x-intercept. So like so. All right, so now I'm going to do one with a hole. The reason I'm going to know it has a hole is if we look at what happens here, minus 2, and we factor the numerator, the x plus 2's will cancel out, just leaving us x minus 2. So what we're going to do is we're going to just graph x minus 2, but we are going to go ahead and do, make sure that we note that there's a hole. So we'll do all of our normal asymptote stuff. But we're also going to make a note that there's a hole. Okay? So how we figure out where the hole is, if we look at the factor that canceled, we set it equal to 0, and we get that x is equal to negative 2. That means there's a hole in the graph at negative 2 comma somewhere. And the reason that is because if we plug negative 2 into this original function, you get 0 over 0, which is undefined. But notice that if you plug negative 2 into the new version of the function, you would just get negative 4. So in the new function, it has a point at negative 2, negative 4. But in the old function, it would be undefined. Okay? So our hole is going to be at that negative 2, negative 4 point. So vertical asymptote, now that our function has been simplified and we have no denominator, there's nothing to set equal to 0, so we have no vertical asymptote. Because the degree of the numerator is now bigger, we have no horizontal asymptote. And our oblique asymptote in this case would technically be the equation of our line itself because there is nothing to divide. Our x-intercept, if we set y equal to 0, we can see that our x-intercept is 2. So at the point 2, 0. And our y-intercept, if we set x equal to 0, we can see is at negative 2. Oops, so it's at the point 0, negative 2. So we have a point at 0, negative 2. There's our y-intercept. 2, 0 is our x-intercept. So you can kind of clearly see what your line looks like right now. We can go ahead and draw that in. But then we can't forget this is the graph with the exception of the place where there's a hole. So I'm going to go to negative 2, negative 4. And at that point, I'm literally going to put a hole, okay, a place that has been removed from the graph. Okay. All right, I'm going to leave that as our graph with a hole, and we can go over some other ones in class on Monday. Now, I just wanted to go through writing an equation for each of these situations. For part A, to write a possible rational function that has an asymptote at x equals negative 3. So x equals negative 3 is a vertical asymptote, so that means x plus 3 must have been in the denominator to get negative 3. And y equals 0, which means there's a horizontal asymptote at 0, so the degree of the denominator is bigger. So if I did that so far, I'd be good, except for then it says there's an x-intercept at 2, which means in the numerator, there's some factor, like x minus 2, that gives an x-intercept. So then I need to do something to my denominator to make it a bigger degree. So I could square this or do something, add in another factor, something that gives the denominator a bigger degree. There's not one right answer in this case. There are many. And then for part B, write a possible rational function that has a hole at x equals negative 1. So that means there must be a factor that canceled out, where if you set it equal to 0, you get x equals negative 1. There's an asymptote at x equals 4. So that's vertical, so there has to be a factor here of x minus 4. So when I set it equal to 0, I'll get x equals 4. I'm going to skip the horizontal one for now. There's an x-intercept at 5. So that means there's another factor in the numerator that comes out to be x equals 5, so x minus 5. And then it says the horizontal asymptote is at y equals 3 over 2. So right now they have the same degree, which means I would use the lead coefficients to make the horizontal asymptote. But right now the lead coefficients would be 1 over 1, and I need them to be 3 over 2. So then that's what I would have in this case. All right, so use this. Use your textbook. Come to class on Friday. You're going to take the quiz. It won't include any of this stuff, okay, because I know this is a little bit more difficult. And then what we'll do is you're going to work on the homework for this after the quiz, and then on Monday we'll answer homework questions.